today we have Irene Spelta from the Universidad de Pavia. She's going to talk on totally geodesic subvarieties of AG generically contained in Torelli Locus.
So, antes hablo en español un poquito para agradecer a todos para la invitación, no lo sé, por la invitación. Y en particular agradezco a Anita por su ayuda y su bienvenida calurosa. Okay, so now I speak in English because I'm not able to speak in Spanish in math. So let's start taking X, a Riemann surface compact of genus G. Are you able to see? Yeah, okay. So we can define the Jacobian of the curve X as the quotient of H naught omega 1 of X dual modulo H1 of XZ, where we have H naught of omega 1 of X dual a complex vector space of dimension G, which is the vector space of the holomorphic one form on X, and then H1 of X is the first homological group, and we see omega 1 of X inside omega naught, omega 1 dual using this map, which sends the class of a loop to the map which sends the class of a one form to the integral on gamma of omega. And this map is injective, and it is well defined thanks to Stokes. So we have that this is omega 1 of xz is isomorphic to z to the power 2g. So it, thanks to this map, which is injective, it creates a lattice of rank 2g in this vector space. And so we have that the Jacobian of x, which from now on we see as a complex vector space modulo a lattice, is a complex torus of dimension G. Okay. In general, when we have a complex torus, we are interested in the fact that it is a projective or not, if it is projective or not. So we have this definition: the complex torus is an abelian variety if it admits an holomorphic embedding in Pn. And we have this theorem, how to check that a complex torus is an abelian variety. We have this theorem, which is due to Kodaira Spencer, I think, which says that the complex torus is an abelian variety if and only if T admits a polarization which is a map Q from V times V in R, alternating and non-degenerate, such that Q of I, U, where I is the imaginary part, V is equal to Q of UV for all UV in V. And we ask also that the Q of lambda times lambda is inside Z. Okay. In particular, supposing to give the description of a complex torus, we supposed to choose a basis for V in V1, VG, and basis for the lattice as L1, L2G. We can always give a representation of the torus in terms of its period matrix, phi, which is the matrix given by the coefficient lambda ij, where we can write this in terms of this. So Li is the sum of lambda ej, vj, from j, which goes from 1 to g. We have the Riemann bilinear relation, which give conditions in terms of the period matrix, which allow us to say that if a complex torus is an abelian variety. And in particular, if it admits a polarization. Okay. If T admits a polarization, we can choose basis for V and for lambda such that the period matrix is of the type delta Z, where delta is a matrix which corresponds to the polarization Q, which is of this type now. Okay. d1 dg, and here we have minus d1 minus dg, and Z belongs to the Ziegler space, where we defined it as the space of the matrix G times G coefficient in C, such that they are symmetric and the imaginary part is positive definite. Okay, and these elements here give the type of depolarization. In particular, when we work with the Jacobian, which is a complex torus, we can always choose a basis for the lattice, which is, in our case, was h1 of xz. We can do the representation of x as a polygon of 4G edges, polygons. Oh, I don't know. Where we have AI, BI, AI minus 1, BI minus 1. We can choose this as a basis of omega 1 of xz. Bj. We can consider the intersection form here. Because we know that these are, if we have our torus, we have the loop, the loop, the loop, the loop. So we have one. And so we have that this gives us a canonical polarization on the Jacobian, because we extend this using the map that I wrote before here. We extend it and we obtained a canonical principal polarization. So we have that the Jacobian of a curve is always a complex torus, a principal polarized abelian variety. And so we can define the map of Torelli J which goes from mg to ag, where we have that mg is the moduli space of smooth projective curves of genus G, and the AG is the moduli space of principally polarized abelian variety, and this map is defined as it sends the isomorphism class of a curve to the isomorphism class of its Jacobians with its polarization. And we have that here an isomorphism acts as a bijective homomorphism of a complex dot of an abelian variety to the other, and it has to preserve the polarization. And so we can see that AG is the quotient of the Siegel space, because always we can represent an abelian variety in terms of the matrix Z, which is here, modulo SP to GZ, where this group acts here in the following way. We have an element here, GD. We have an element which represents an abelian variety, and the action is this, -1 V plus VZ. And so this gives us the isomorphism classes here. Okay, we are interested in particular in the image of the Torelli locus, its closure inside AG. Because we have a conjecture from Coleman and Oort, which says that there do not exist we call them positive, no, positive dimensional subvariety positive and spatial of a G generically contained in the Torelli locus in J and G closure for genus G greater or equal than 0. I have to explain these words. Okay, suppose to call Z a spatial subvariety. We have that Z is a spatial subvariety if it is Z inside AG is totally geodesic. And now I will explain this definition. And then we have to ask that Z contains Chi endpoints, which is an arithmetical condition which says that Z is inside AG, supposed to have the class of a simple abelian variety. Here we say that this point is a Chi endpoint if we consider the endomorphism algebra on the rational of A, it contains a subfield K such that K as degree is an extension of Q of degree at least 2G. What's the definition? What about the definition of totally geodesic?
CM field or something like that?
Is it asked to be a field? I think yes.
To be special, you need both conditions?
Yeah. Spatial or Shimura is the same. Spatial subvariety is the same as Shimura subvariety. Okay. Okay. See, is totally geodesic supposed to have MG, a Riemannian variety. So this is the metric. We can say that n inside M subvariety is totally geodesic if every geodesic of n is a geodesic of n of m. Okay, here we have the matrix, here we have the induced matrix. We check that if we have a geodesic with respect to the induced matrix here, it has to be a geodesic also here. In our case, we work in AG, but we know that the Siegel space is an homogeneous space. So it admits a canonical matrix, which is the canonical matrix of the Siegel space. Admits canonical. This passes to AG, and we say that Z inside AG is totally geodesic. If there exists y inside AG such that pi of y is z, where pi is the quotient mark from Siegel to AG. The idea is that with respect to this metric, the Jacobian locus, the Torelli locus inside AG is expected to be very curved. So we cannot have for genus G higher than 0. Yeah?
What was the last definition? So Z in AG is a totally geodesic?
If there exists a y inside the Siegel space such that you have that the image of y is z. You have always to check
And
that.
Y has to be what?
Y?
Y, what is what?
Ah, yeah, totally geodesic.
Okay.
Sorry. The idea is that we cannot have a big number of totally geodesic subvariety of AG for genus G greater or equal than 0. And in fact, we have examples of them, and the examples known so far are 40, I think. And they are all in genus less or equal than 7. We don't have examples in genus higher than 7.
Is, in this case, is totally geodesic the same as being a Kuga variety? I think
Ooh, I don't know.
that's
No,
like
I
this,
don't say.
The orbit of a subgroup of SPR or something like that?
I don't know.
Does it have something to do with having an infinite number of CM points?
If you have one, you have infinite number. Someone proved
If
it.
it is special.
Yeah. If you can find one, you have countably many, I think.
Okay.
Yeah. So you have only to check that you have one CM point. The examples that we know are all constructed as a family of Jacobians of curves which are Galois coverings of P1 or of an elliptic curves. The first were found by the Young and Oort, presented first examples. Of totally geodesic subvariety obtained as Jacobians of curves which are Galois cyclic coverings of P1. Then we have Monen, who gave the complete list of this type of Galois coverings. In 2015, then we have Frediani, Gigi, and Penegini, who found the first new examples with Galois coverings of P1 where the group G isn't abelian, non-abelian. Galois coverings. And also, in that work, they presented a sufficient condition which ensures Shimura subvariety, and we will explain this sufficient condition. And then in 2016, Frediani, Penegini, Porru found new examples as Galois coverings of an elliptic curve. How did they find these examples? We try to explain this. Oh. Okay. Suppose to have C, a curve or a Riemannian surface of genus G. Then consider G a finite group of the group of the automorphism of the curve. And then we consider the action of the group on the curve. Suppose that this is the quotient, this space of orbits, this is F Galois coverings with the Galois group G. Then we have supposed to call T the vector of the branch points. And then the vector of the local monodromy. Okay. We can say that starting from a Galois covering, we always have a branch point and branch points if we have, and these. So we can always describe a Galois covering in terms of this vector, which is called a sort of datum, and Riemann existence theorem ensures the possibility to pass from this one to the Galois covering, where we call from now on this CT because we want to recall that T is the vector of the branch points. And the Riemann existence theorem ensures also the possibility to do the same in families. So supposing to move these branch points, we obtain a family CT, where T is the branch points, families of Galois coverings, which are parametrized. We have to be more precise, we have to work at the level of the Tate-Muller space because G is inside the automorphism of the curve. So we can see it inside the mapping class group because it is defined as the quotient of the isomorphism of the curve which preserves the orientation modulo diffeomorphism isotopic to the identity. And we know that the mapping class group acts on the Teichmuller space, and we can show that our family is parameterized by, we have this action, so we have that, I don't say this, starting from the Teichmuller, we act with the mapping class group, and so we arrive to the moduli space, and so we obtain that our family CT is parameterized if we call this map by prime by the image of the fixed part of the Teichmuller space if we consider the action of this group induced here. We call from now on this MG to recall the fact that we started with this. And this is a space of dimension 3G prime minus R plus 3. The dimension of this, the M of M is equal to this. A theorem from Frediani, Gigi, Penegini says that if this is the sufficient condition, if call it star, if M, which is the multiplication map which goes from S2 of H naught KC, when we take the G variant part, to H naught of 2KC G invariant, is an isomorphism, then we have that the image through the Torelli map of MG of our locus closure, which we call Z of MG, is a Shimura subvariety of a G. A remark that we can say, that we can do, is that here we ask for the subjectivity and for the injectivity of the map, but from Griffiths we have that I forgot I think. We have that the differential of the Torelli morphism is the dual of this map. And we know that Torelli morphism from mg naught, now I see what is this, where mg naught is mg minus the hyperelliptic locus in genus G is an immersion. So here we have to check only for this is, and the differential of this map is injective, so this is differential is adjective, so this is surjective, and so we have to check only the injectivity of this map. And so if we have that the dimension of S2 K H naught of KC G is equal to the dimension of this space, which is the dimension of our family, which is M3G prime minus R plus 3. We are done.
So you want the upper map to be surjective, right? Yeah, that's it? The map up there, you want that to be surjective then, for it to be an isomorphism. Is that it?
You have to, this is injective, so this is injective.
Yes,
Yeah, so it has to be.
Yeah, never mind.
Because it's the dual. We are okay.
So
And
it worked for any G prime as the genus of the total quotient. I thought it was over
yeah,
P1.
yeah. they proved it they prove it in genus G equal to 0, but then Frediani, Penegini, Porru, they proved that this is okay also in case of G prime greater or equal than 0. And so, using this, they wrote a computer program, and with Magma, they found all the examples that satisfy this condition.
But it is still Fisher condition.
Yeah, this is the problem. So, okay, in 2016, Frediani, Penegini, Porru proved that the same is true for genus G strictly greater than 0, and they found new examples with G prime equal to 1. They found new examples, so here the quotient G prime, we have to go to C, G is an elliptic curve, and they found 6 examples, I think. And okay, also they proved that if M is a family which parameterizes Galois covariance of this type, which satisfies star, and the genus is greater or equal to 1, then we have that the genus G has to be minus less or equal than 6G prime plus 1. So if, for example, the genus G prime is equal to 1, we have that the genus G has to be less or equal than 7. So we cannot have examples of Shimura subvariety obtained in this way with genus G greater or equal than 8. So this is in agreement with the Coleman and Oort conjecture. Okay, so here I was supposed to present an example.
With the computer program, did they find all the examples for all G prime?
They checked it for G prime equal to 1, but we proved another bound that I will speak it later. And I think yes, but the question is that they proved and they controlled that using the condition which is only sufficient. An example that I want to explain, for example, suppose to take the family of the curve xt created as a curve which are the normalization of this equation. We take y5, x minus 1 plus 1, x minus t squared. We have this exponent, so we have to work with the normalization to obtain smooth curves. This is xt is a one-parameter family of genus 4 curves. Here we consider the action of the group G, which is isomorphic to Z phi, generated by Xz, where Xz is e to 2 pi I phi. And we consider the action of the group G on the curve which sends xy to x zy, and xt, the normalization. we have to be more precise, xt tilde modulo G gives equal walk covering of P1 where the group G is cyclic, and thanks to the fact that it is cyclic, we are able to give the equation of the curve. If not, I'm not able. And okay, so we consider the monodromy map, which goes from pi 1. We have that the branch point of these coverings are 0, 1, minus 1, and t. So 0 plus or minus 1t. Then we go to the group. We consider a loop around the branch points, and so we have that we have 4 branch points, 4 loops. This goes to the order, which is 1, the class inside 5, and the same for the loop where we have that gamma 1 is the loop around 0, gamma 2 is the loop around 1, gamma 3 is the loop around minus 1, 0, 1, and the last one around t. So we have that gamma 2 goes to 1, the same for gamma 3. 5. And gamma 4 extends to modulo 5. Okay, using this, we can use Chevalier formula. Because we have an action of the group on the curve, we consider the representation on the group of the holomorphic, on the space of the holomorphic one form of the curve. And using this, we have a decomposition of H0 Kc as a sum of vectorial space Y, where Y is the space of the omega of the one form such that rho G applied to omega is equal to C to the power I omega. Chevalier formula gives us the dimension of the Y, and it says that the dimension of Y is equal to minus 1 plus from 1 to 4 the class modulo 5 of I and the image AI, where AI is this number, the class of it is M of gamma I think. Okay, so we can check that the dimension of V1 is 0, the dimension of V2 is equal to the dimension of V3 and is equal to 1, and the dimension of V4 is equal to 2. And this is okay because we are in a curve of genus 4, so this has to be of dimension 4. And so now we have to evaluate S2 of H0 Kc, the G invariant part. This is S2 V2 plus S2 V3 plus S2 V4 plus the mixed tensor product V2 times V3 plus V2 times V4 plus V3 times V4. But here we have to take the G invariant part, so here we have Z to the power 4 to 2. Here we have Z to the power 6, so Z. And so we can say that the remaining part is that V2 times V3, so it has dimension 1. So it's okay, because our family depends on one parameter, so it is a one-dimensional family, so we are okay. And so considering the family of the Jacobian of these curves, we obtain a Shimura curve gives a Shimura curve in A4. Okay. What I'm doing at this moment, I'm trying to understand with Paola if star is also necessary. We don't know. We are trying to, we don't know how to prove it because Monen, I think, proved that star is also necessary in the case of the group G cyclic, but he used techniques of Charpy, and so we are not able to use these techniques in the case of a general group. And in order to proving that it's not necessary, we are trying to find new examples of Shimura subvariety. And we are working on completely decomposable Jacobians. This is the reason why I'm here, because we are trying to start from Jacobians which are completely decomposable and try to understand the terms of the decomposition and try to calculations. In fact, another thing that I'm trying to do is to study the Jacobian decomposition of the family which are Shimura, which give Shimura subvariety in AG. So I'm studying the families of Paola and the others, and I'm studying the decomposition, the group algebra decomposition of that families, because I found that almost all are completely decomposable, but not all. For example, this is an example where I'm not able to decompose the Jacobian, and so I'm asking something to Anita. And because if I'm able to decompose all of them, probably this is the space, the correct space where we can look for new examples, but we don't know. And so we are trying to do computation. During this computation, we proved two things. The first one is that supposed to call MG inside MG family locus which parameterize I don't know how to say subvariety which parameterize Galois coverings in the setting, in the previous setting, where G is the Galois group, G is the genus of C, and G prime is the genus of C prime greater or equal than 1. Studying the multiplication map, we proved that G prime has to be less or equal than 3. And so, as a corollary, we have that.
That's for what? For what does G prime have to be less than or equal to 3?
Because.
Is that for condition star to be satisfied?
Yeah. I asked that it has to be satisfied. Oh, sorry. which so if it satisfies a star, we have that M is in an isomorphism, so we can work on the dimensional. And so all the examples in these settings are that already found by Frediani, Perentini, Porro, because we didn't find examples where the genus is equal to 2 or equal to 3. And also we proved we started from a result of Gruszewski, I don't know if that's the correct spelling, and Muller, who studied one of these families, and they said that it is fibered in totally geodesic curve. We extended this result because we proved the following proposition. Supposed to have MG, G, blah blah blah. So it is a family family of Galois covering which satisfy the star, and the genus is greater or equal than 1. Then we can define the prime map from MG to AG minus G prime with its polarization, which sends a point here is Galois covariance. We associate the prime variety, which is isogenous to the Jacobian of the curve modulo F star G prime. It is a result due to Monen, I think, that the Jacobian of the curve is isogenous to the Jacobian of G prime times prime C prime when we have a situation like this. Okay? Okay. Considering this map, we studied this map, and we obtained that M is fibered in totally geodesic curve because the fiber, we proved that the fiber has dimension G prime plus 1 alpha. And so, thanks to the fact that the examples that we know of M which satisfy star have always G prime equal to 1, which is equal to 1, and so corollary, all the examples of Frediani, Perentini, Porro are fibered through their prime map. Map in totally geodesic curves. And sometimes we are able to understand the fibers thanks to the fact that I studied the decomposition of all these families. So I'm able to see when a family has the prime which is fixed. So I'm able to see, oh yeah, this is a fiber. And I think it's all.
Any questions? Are you hoping to maybe find counterexamples to the the converse by using this prim map, or
Contraexample to
I mean to
the
show that the converse is not true of star.
no, I don't know.
Because you said that Mullen proved that n,
Yeah.
your star condition is necessary.
In the case of
In the case of abelian groups or
of cyclic groups, yeah.
But what do you expect in the other cases? That it's true or?
We don't know. Because the idea is that we don't know if it's true or if not, and so because we are not able to prove that it is a necessary condition, we are trying to find examples which allow us to say that it's not necessary, but we don't know.
And you have examples of that kind yet?
No, we don't have.
What exactly did Grushevsky and Moeller prove?
That one of this family, of the family of Frediani, Kenegini, Porro,
So you
is
proved that
fathered.
all of them?
Yeah, we
nice.
proved that all of them. Yeah,
And you found that all of the examples were like that?
we found all the examples are already known.
Yes,
Yeah.
but you proved that all the examples are also fiber.
Yeah,
as
yeah.
They said that.
Yeah.
One.
Yeah. There are only 6 families. They are not. A lot.
So- And you are studying now the decomposition. I mean, because you mentioned that Frediani and the others had a table with all the examples. I mean, all the families of Shimura
Subvarieties, yeah.
up to genus something.
Yeah.
So you are studying all those Jacobians and see if they are completely decomposable
Or not. Yeah. And the examples are 40, 50, I don't know, and 35 are completely decomposable. So I hope
Because
that.
when you stated Coleman and Oort conjecture, you said that you want this special subvariety to be generically contained in the closure of the Jacobian.
Yeah.
And do you want something that the
No,
intersection
yeah. This is the generically contained. I didn't say it. Huh? I don't know. Okay. I asked that the intersection is non-empty, so I want that. Yeah.
Is there any maybe Coleman conjecture for prims, for example?
Coleman conjecture? I don't know. Are you asking for totally geodesic subvariety inside the prim locus?
Yeah, in the prim locus.
Frediani, Penegiti, and Porro proved found examples of totally geodesic subvariety inside the prim locus, but
With CM points, or?
I don't know. I think yes, because if I remember correct, the title of the paper is Shimura Subvariety, so I think yes.
Any other questions? Okay, let's thank Irene again.